Here we go. We're going to talk about rotation revolution and what those words are and what they kind of give us here on Earth. So I'm going to jump right in. Clearly, we're looking at the rotation revolution part 2 PowerPoint that is found on Google Classroom. So, tilt. Our Earth is tilted at a 23.5 degree axis. As you can see here, that's the tilt, and that tilt really is half of the reason why we have seasons on our planet. Seasons that are winter, spring, summer, and fall. Okay, so yeah. So we have the tilt, and so we can talk about what happens here as we spin. We call that rotation. It takes 24 hours for it to spin. That means, obviously, 24 hours. So you have 1 hour, 2 hours, 3 hours, all the way to 24, and then you are back to the same time you were yesterday. And you'll obviously go through daytime and nighttime during that rotation. While the Earth is rotating, it's also revolving. We also call that revolution or orbiting, but it all excuse me, it all means going around, and it takes 365 days for it to revolve around. So in fact, it takes 365.25. That's why every 4 years we have a leap year, and we gain a day in February. So, but we round that 365, and that's how many days that we have in a year. So rotation, spins, and revolution, the fact that as the Earth is spinning, it's also going around the sun, those two things right there, tilt and revolution, is what causes seasons on our planet. That is very testable. Make sure you have that. Okay. Let's scroll on down. Different seasons occur depending on the time of year and whether you live in the northern or southern hemisphere. So let's talk about a couple of things that happens here. You can look at the northern hemisphere and the southern hemisphere there. Each one highlighted in black, just so you can see which one's northern, which one's southern. So December 25th, obviously, you guys know that as Christmas. It's cold. It's during winter. During that time, our Santa is clearly decked out in red and white suit, whereas the southern hemisphere, they have Christmas at the same time, but instead of Santa dressing up in that red and white suit, he probably has on a little red Speedo or something along those lines because it's really warm outside. So just remember, those are the things that are going on. I know that our experiences in the northern hemisphere are what they are, but remember that it's completely opposite in the southern hemisphere. So when it's winter for us, it's summer for them. When it's summer for us, it is winter for them. Here we are on the next screen. The question here says, when it is July in Texas and it's summer, it is winter in July in Australia. Why? Well, I just talked about that. Well, no, actually, we could talk a few more details about this. As it is summer in the northern hemisphere, let's see if we can look here. Here's a great picture. We're just focused on this picture here. Summer in the northern hemisphere. It is tilted clearly 25 degree or 23.5 degree axis. You can see that northern hemisphere, if we draw a little line here where the equator is, you can see that the northern hemisphere is tilted towards the sun. So it's getting that, look at that arrow, the direct rays are hitting the northern hemisphere. And I talked about that in class on how you take a flashlight and you put it in somebody's eyes, it's intense, it's bright. But if you glance it or tilt it away, it's not as bright. That's the same exact phenomenon that's happening with the sun, and what causes our sun to be, during the summertime, very hot, and during the wintertime, it's still super cold outside even when the sun's in the sky. So that's the difference between direct and indirect light, direct and indirect energy, and in this case, direct and indirect thermal energy. So that's the reason why during the summer it's hot for us, and during the winter, and this picture here is it's colder in the southern hemisphere. And then 6 months later, flip-flop, now it's winter for us and summer for them. So just make sure you read through this and that this makes sense to you. Okay, moving on. All right, love this graphic. So once again, whenever I'm looking at these graphics, I always want to find summer in the northern hemisphere, and I found it. It's right here. And I always draw my little imaginary equator so I can really get an idea of what's happening, and that northern hemisphere is tilted towards the sun. This day is the summer equinox. Happens right around June 21st through the 23rd. And then 6 months later, boom, here we are, December 21st through 23rd. Winter in the northern hemisphere, now summer in the southern hemisphere. Okay? Is with that, again, a little idea about what the direct sunlight does. Smaller surface area, more intense. Versus the winter, it's a glancing, larger surface area, so less intense energy on that specific hemisphere that's getting that indirect sunlight. Because when you see this, the other hemisphere is getting this. So if this is the northern hemisphere, this is the southern hemisphere. And then 6 months later, this is now the northern hemisphere, and this would be the southern hemisphere. All right. Everybody needs to be able to do this. First of all, what you do is you off to the side, you'll write the order of the seasons: winter, spring, summer, fall, and then you just follow it. So let's locate summer in the northern hemisphere. Right here, point A, northern hemisphere, summer. This will be June 21st through 23rd. 3 months later, during this trip around the sun, here we are. We went from summer. What's after summer? Fall. Here we go. We're fall here. And then here will be winter, 6 months from point A. And then 9 months from point A, bang, spring. That's right. And then 3 months later, another year has passed. Okay. And then what you do is just make it opposites in the southern hemisphere. So here we would write winter, spring, summer, and then fall. So let's talk about the hours now. You've heard me mention in class once or twice at this point that when it's summer, our days are longer, and when it's winter, our days are shorter. Now check it out. You can totally see. Look at the North Pole here. It's tilted towards the sun. As the Earth is spinning and rotating, it's got sun for 24 hours. If you were up in the North Pole and you were sitting there looking at the skyline, you would see, and if you sat there for 24 hours, you would just watch the sun go around the sky. And then take a plane trip all the way to the southern hemisphere. You're in dark. It's dark for 24 hours. Look at it. As the Earth would be rotating, you're sitting here, you're not getting any of that sun's rays. So it's dark. Okay. And then check out the equator. Here's the thing about the equator. It's always getting just slightly less than um, direct sunlight. Slightly less. But it's always getting, that little bit of direct sunlight all year around. That's why when you look at that band right around the equator, that's where the warmth really is absorbed from Earth. That water, nice and warm right around the equator. That's where the hurricanes are born, right around the equator. But anyway, so let's look at it. We got 24 hours of daylight, 0. And as you work your way down, you will get less and less hours of daylight all the way to here. So 12 hours of daylight. Always look at 12 hours of daylight right here at the equator. So 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. See how that works? And then from 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's how that works. And that's June 21st through 23rd. So it'll start its trip. Let's say it's starting from here. It just starts to revolve around as it's rotating, spinning and moving. So June, July, August, September. Okay. Now what we call this is the autumnal equinox in the northern hemisphere. Equinox, 12 hours of daylight from pole to pole. That day, everywhere on Earth is getting 12 hours of daylight. That's an equinox. Equinox is equal daylight hours all the way down. And so we're just going to keep going. September, October, November, December. Oh, November. Happy birthday, Mr. Camacho. Here we go. Bang. Now we're at December. December 21st through 23rd. It's now the winter equinox the winter solstice in North America, summer solstice in Southern America. So now, whereas the North Pole was getting 12 hours of daylight, now it's at 0. Now the South Pole is getting the 12 hours of daylight. And it just flips. So 24 to 12 to 0. And over here, 24 to 12 to 0. See how that works? Now our daylight hours here in Texas are probably sitting at about 9 hours of daylight. Versus over here was like 14, 15 hours of daylight on that day, longest day of the year. Shortest day of the year. So it's December 23rd, keep going around, December, January, February, here we are, February. This is where we are in our trip around the sun this year. And then we're coming up to March 21st, after spring break. Equinox. We will call this the vernal equinox in the northern hemisphere. Autumnal during autumn or fall. Vernal during spring. But the same concept, 12 hours of daylight all the way. The heat is distributed evenly. Check it out. If your band of warmth is right here, do you see what's happening? It's splitting between the hemispheres. So we have equal heating and equal daylight hours in the northern southern hemisphere. So energy is distributed evenly during this time of year. The hours are distributed evenly during this time of year. It's fair weather for the most part in both hemispheres, except for up here and down here. Still soup's cold. Well, greenhouse effect. We got ice melting everywhere. But anyway, in theory, this is what's supposed to happen to a healthy Earth, friends. And we go around. I hope this kind of makes sense. But definitely practice when you see something like this, being able to label it. I'm able to label Northern Hemisphere, summer, right here, June 21st through 23rd, longest day of the year, and then opposite, winter solstice, shortest day of the year, down here. and then label both hemispheres all the way around. Every one of you needs to be able to successfully accomplish that. And that, my friends, is how we have seasons because of the phenomenon of rotation and revolution. Thanks for listening.